Hi everyone, we are discussing the numerical methods and integral transform course. In that course we are at the Fourier transforms. In that Fourier transforms we are discussing infinite Fourier transforms. So in this video we will discuss what is infinite Fourier transform and what is infinite Fourier sine transform, what is infinite Fourier cosine transform. For these three transformations we will take the formulas, and in this video we will take some examples, some problems on the infinite Fourier transforms. In the next videos we will go for the infinite Fourier sine transform and infinite Fourier cosine transform with the examples. So first we will take that standard formulas of infinite Fourier transform, infinite Fourier sine transform, infinite Fourier cosine transform and its inverse. So first one, infinite Fourier transform and its inverse formula. So we have the standard formula that Fourier transform of a function f of x is given by Fourier transform of this f of x, which is given as integral minus infinity to infinity f of x into e power ipx. So here the meaning of this one is, suppose I have given a function f of x, and for this function you apply the Fourier transform, and once if you apply the Fourier transform, this function will be converted in terms of f of p. Okay, so now we'll see when we can apply this inverse Fourier transform. So in the Fourier transform, first we have given a function f of x. By applying the Fourier transform for f of x, we got the value of f of p. Now reverse. Now I will give the value of f of p. Now for this f of p, you apply the inverse formula and we have to get the function f of x here. Reverse. Here in the first case I will give the function f of x, apply the Fourier transform and get the value of f of p. Now in the second case, instead of giving f of x value, I will give the value of f of p, and for this f of p, by using this f of p, we have to get the value of f of x, for which function we have applied the Fourier transform in order to get this f of p value. So whenever f of p is given and if you want to find out the value of f of x, then we have to take the help of inverse Fourier transform formula. Okay, so that formula is given by f of x is equal to 2 by pi integral 0 to infinity f of p, that will be given in the problem, and e power minus ipx into dp. So these are the formulas, Fourier transform and its inverse Fourier transform formulas. And similarly, along with this Fourier transform, you are having Fourier sine transform and Fourier cosine transform also. So now we will take the formula for Fourier sine transform and its inverse formula. In the problem itself, they will mention whether we have to find out only Fourier transform value for the given function, or whether we have to find out only Fourier sine transform or Fourier cosine transform. That will be mentioned in the problem. No need to worry about that. So this Fourier sine transform is represented with capital F represents the Fourier transform and the suffix s represents the sine. So capital F suffix s represents the Fourier transform, Fourier sine transform of that particular function f of x. So f suffix s of f of x is equal to, and that value is represented with f suffix s of p, which is given by integral 0 to infinity f of x into sine px dx. Okay, so now reverse. I have given Fourier sine transform formula value, and for this we have to get the f of x value here. Now whenever Fourier sine transform value is given, now by using this value, if you want to get f of x value, then we have to take the inverse of Fourier sine transform value formula only, because we are taking Fourier sine transform value. So by using this, if you want to get f of x, we have to take the inverse Fourier sine transform of that f of p. So that is given by 2 by pi integral 0 to infinity f suffix s of p, that will be given in the problem, and sine px into dp. Okay, these are the two formulas here. And next, if you want to go for the Fourier cosine transform, so this value is given by So since we are saying infinite, so since it is an infinite formula, so we are taking that integral limits at 0 to infinity. If you observe that clearly, it is very understood that for all the integrals we are taking the limits at 0 to infinity. So that's why we have taken as infinite. And next, similarly, this is our inverse Fourier cosine transform value here, that is represented with f suffix s of p, f suffix c of p is given by. So this is the value, this is the formula to get that f of x value by using Fourier cosine transform value. Now let us take problems on that first case, that is Fourier transform. So in the problem, like directly they will mention find the Fourier transform of that f of x defined by this. F of x is equal to has given. So we have different values for f of x. One is 1 minus x square whenever that mod x value is less than or equal to 1, and we have another value for f of x, that value is equal to 0 whenever that mod x is greater than 0. So first we have to find out the Fourier transform of this function. By using that Fourier transform of that function, we have to get this integral values here. So whenever we want to prove any deductions or any conditions or any integral values, after finding that Fourier transform for the given function, in order to prove this integral values, we have to go for the inverse formula. We have to take the inverse of Fourier transform formulas. Not only in Fourier transform, suppose if you are in the Fourier sine transform, then we have to take the inverse Fourier sine transform formula and we have to prove these deductions or conditions. Now let us see how to get this Fourier transform value, and by using that Fourier f of p value, we will see how to get this integral values here. So given that this is our function here, now first we have to understand what does this mod x less than or equal to 1 represents, what this mod x greater than 1 represents. First we will take that. So f of x value he has given as 1 minus x square for this condition mod x less than or equal to 1. So this mod x less than or equal to 1 represents this one, like minus 1 less than or equal to x less than or equal to 1. So this mod x less than or equal to 1 means that x value lies between minus 1 and 1. And similarly the second condition, f of x is equal to 0, mod x greater than 1, this represents that two conditions here. One is minus infinity to minus 1 and 1 to infinity here, because we defined that function minus 1 to 1. So entire minus infinity to infinity, this condition is completed, so we have to take the remaining two conditions here. So minus infinity less than x less than minus 1 and 1 less than x less than infinity. So these are the, so by using this we have converted into the conditions here. Mod x greater than 1, it represents that x takes the values from minus infinity to minus 1 as well as x takes the values from 1 to infinity. These are the conditions we have to remember for this mod x greater than 1. Now according to these conditions, we have to take the Fourier transform and we have to split this integral limits minus infinity to infinity into three conditions here. One is minus infinity to minus 1, minus 1 to 1 and 1 to infinity. So minus infinity to minus 1, we got that value is equal to 0, so replace that. And whenever that x lies between minus 1 to 1, we can take that f of x is equal to 1 minus x square, which is given in the problem itself. And whenever that x lies between 1 to infinity, then we can take that integral value is equal to 0. So 0 into anything equal to 0, integral of 0, first integral and this third integral gets cancelled, vanished, and you will get only the second integral which is remaining here. So minus 1 to 1, 1 minus x square into e power ipx and dx. If you complete that integration here, apply uv formula here, integral of uv, and then substitute the limits minus 1 to 1 here, then we can get our required value here. So this is the uv formula we have applied, substituted. So finally we will get this integral value here. So we know how to, we have explained number of times how to apply that integral of uv. Apply that integral of uv and then substitute the limits here, then we can get our required value here. So now here we are having, so remove these brackets by multiplying with this, you will get I into p square and I square into p square. So I square is -1, so we can take that minus to the numerator, and this, now here this I and this I gets cancelled, so finally we will get Laplace transform, this Fourier transform of f of x is equal to 4 by p cube minus p cos p plus sin p. This we can consider our capital F of p value here. So this is first case. The first case is for the function f of x, we got the Fourier transform of that f of x, that value is represented with f of p. Now by using this f of p, we have to get that integral values here. Second part, reducing that integral values. So by inverse, already we said that in the beginning, whenever we want to prove any conditions or any deductions, then we have to take the help of inverse formula. So we have, you take that inverse formula of Fourier transform. So this is our formula. Replace that f of x here, whatever the value we got in the previous slide for f of p, replace that, and f of x, in the problem itself he has given that f of x is equal to this value. Take that value f of x as it is, which is given in the problem. Now you concentrate only on this part, LHS. So keep x is equal to 1 by 2 in this. So 1 by 2. So here, so by substituting the suitable value for x, we can reduce that. So by substituting this, we got this one. So 1 minus, why we are taking this condition here, only this one. The beginning only we said that modulus of x less than or equal to 1 is represents -1 less than or equal to x less than or equal to 1. So but whatever the value we have taken for x is equal to 1 by 2, that 1 by 2 lies in this condition, satisfies this condition. So which for this condition, that function f of x has given as 1 minus x square. So 1 minus x square, 1 by 2 whole square, that is 1 by 4. You will get that value is equal to 3 by 4. Now simplify this. So you send this and you constant this to this side. Simplify this, you will get 1 by p cube into p cos p minus p. And we have the formula e power I theta. In the lower classes we have seen e power I theta equal to cos theta plus I sin theta. And similarly, e power minus I theta can be written as cos theta minus I sin theta. So in place of theta here we are having p by 2. So cos p by 2 minus I sin p by 2 into dp. Now remove these brackets and equating the real part on both sides, we will get our required value here. So this is our integral. So since this is an even integral into even function, inside this integral we are having an even function. This entire function is an even function. So this integral 0 minus infinity to infinity can be written as 2 into integral 0 to infinity. That value is given by minus pi by 8. Now send this 2 to this side, it becomes minus 3 pi by 60. And if you want to reduce the second condition, put x is equal to 0 in the standard formula, you will get this. So in the first condition we have taken f of x is equal to 1 minus x square. This is valid, -1 less than or equal to x less than or equal to 1. We are taking x is equal to 0, which satisfies this condition. So in this you substitute x is equal to 0, you will get our f of x value here. Send this constant terms outside and send that constant terms to this side, you will get this. And so that whatever the function you are having inside the integral minus infinity to infinity, that entire function is a even function. So this even function integral minus infinity to infinity can be written as 2 into 0 to integral 0 to infinity this. So this is our required condition here. So like this we can use our infinite Fourier transform. So how can we identify whether that problem related to infinite means? Based on the conditions. So in the problem, if the conditions are not mentioned, that means the range of that x is not mentioned, by default we have to go for the infinite Suppose if that if the range is mentioned like 0 less than x less than 1, so the x lies between in the limited range, so then we can call it as a finite. Then we have to choose based on this range or that interval, we have to decide whether we have to go for the infinite or finite. So in this we have seen how to apply the infinite Fourier transform, and in the next video we will go for the infinite Fourier sine and cosine transform. Already we have taken formulas on this Fourier sine and cosine transforms in this video. Now let us take some examples on these both concepts in the next video. Thank you.